Here's our air handler. Air from the building is coming in here. Maybe it's coming in from the top here and then connecting down here. Air from the building is returning here. It's there might be a duct that opens up into the ceiling like this, and all that ceiling air is returning into this mechanical equipment room. Sometimes it's ducted to the machine. Sometimes it just discharges into the mechanical equipment room, and the mechanical equipment room is under negative pressure. In here, you might have a fan. First thing you see there might be a fan, right? So I'm going to move that fan over a little bit in a second. Okay, I'm going to put the fan over here. Okay, so this fan, this is under a negative pressure, right? Static pressure is negative here because it's getting pulled along by the fan. So now, downstream of this fan, we might have a filter bank. And this might be these silly little box filters. They might only be an inch thick. And, they catch like butterflies and, and shoes, that kind of stuff. They're not really very efficient. However, when there's a lot of pollen outside, when the air's bad outside, they always tell you to stay indoors, right? With the air conditioning. Because even though they're not super efficient, remember the air from this space is going over these things. We're getting 6 air changes an hour in this room. So every hour it's going through those filters 6 times, right? So over time, these catch a lot of material over time. In fact, as they get a little dirty, they get clogged a little bit. They even actually get a little bit more efficient over time. If you got a really good building, a really good architect, building wants to spend a little money, they'll put a higher efficiency filter in here. There's a standard for rating filters. This higher efficiency filter, what it has a pleated filter. Kind of looks like a cloth-like material, but it's pleated. Problem is that once you go from this lower efficiency one to this one that catches more dirt, it resists flow. You're going to lose flow. So why do you think they pleat it? You get that flow back by increasing the surface area of the filter. That's why they're pleated. That's why they look pleated. And some systems have even more elaborate and thicker. These are usually 2 inch thick and they're pleated. Okay, and there's a standard for these, MERV 1 through 14. One of these slides is going to describe the filters, how they're assigned and stuff like that. Pretty good filter. A pretty good filter is a MERV 8. A really good filter is like a MERV 10. Right? So as you go up in numbers, they become more efficient. Okay, so anyway, so now you got that filter, right? That filter, somebody comes in, changes that filter every once in a while so they don't clog up. Downstream of that, you have a coil. This could be your cooling coil, for instance. That could be a chill water coil. You send cold water through here, the air gets cooled as it goes through here. Downstream of that, or even maybe butted against it, you can have another coil. This could either be a hot water coil, or it could be a steam coil. That's to heat the air. And then this continues along, and it goes up, and it gets distributed up into the ceiling, and you get like a network of ducts coming off it. Here's the unit. You have a network of ducts, big duct that comes out, gets smaller and smaller as you go along, and ducts come out to either side of it to supply various offices and classrooms or whatever you're doing. So it's a whole network of ducts that come off of that. Okay, now on the suction side of this, we're under a negative pressure. So if I take a small duct, connect it here, and run it to an outside wall, right? What happens to the fresh air on the outside of that? It gets pulled in here. That's your fresh air intake. And what they'll very frequently do is put a damper, right? A device to control the flow, and that might be motorized, right? And it might be motorized so that you can control the percentage of air that comes in through here. And what's pulling the air in, it doesn't have its own fan. What's pulling the air in is the negative pressure on the suction side of that fan on the air handler. Now, if you're pulling air in from outside, what do you have to do with the air that's already here in order to get that air to come in? You got to get rid of some room air, right? One of the ways that they do that is they rely on elevator shafts, bathroom exhaust, various devices in the building, lab hoods, to get rid of the air from inside. So they don't bother to do anything beyond to supply that fresh outside air duct, right? Many buildings, they don't have enough exhausts, enough losses inside the building to account for that. So what they'll do is, on the pressure side, they'll have a duct that goes outside and discharges air at the same rate that you're making it up with fresh air. Okay, a lot of times this is called a fresh air intake, and this is called a spill because you're spilling air out to make up for the fresh air that you're pulling in. So that's what you should see on all of these systems. You should see the fresh air intake. You should see the damper that controls it. And you may see sometimes that these are all closed down. Now, why would an air conditioning guy in the summertime close those dampers down? Well, maybe this coil is undersized. Maybe the office that was originally designed for occupancy by 100 people now has 175. And maybe they have twice as many computers as they originally designed it for. What happens? You can't cool the space. So anytime you pull in warm outside air, you have to cool that. You lose capacity. So sometimes they'll close this because people are complaining that it's not cool enough. And they can cool more effectively if they close the fresh air intake. Close the fresh air intake, now you start to build up contaminants, right? So you're kind of fighting yourself. Wintertime, same deal. You know, like you can't get it warm enough, people complain it's too cold. The other reason they might open or close this damper is that the building manager, maybe costs are a problem right now. So what happens in the wintertime when you pull in cold air and you have to heat it? It costs money. Right? Even worse in the summertime, you pull in hot air and you have to cool it. Right? Costs even more money. Right? So you significantly impact your cost depending on the percentage of outside air that you pull in. So you got to fight. You got to fight between comfort, and capacity for the unit, right? That's indoor air quality guy. One of the things you look at when you look at the drawings is you look at, gee, I see. Look at what there's twice as many offices here as they show in the drawing, the original drawing. Oh, we added that on. We had to add on. Needed more space. You know, we added that stuff on, and so on and so forth. You can get kind of a feel for. And even just looking, sometimes you can see people packed in like sardines or something like that. And other offices where, there's a mile between every desk. So you get kind of a feel for, what how functional the HVAC system might be. And that's one of the things that you look for. So let's go back to these slides. Okay. So what are the things that we're looking for? What generates these complaints? Well, what's good indoor air quality? Start with that. Lack of offensive odors. CO2 levels approximately the same as outdoors. That's nonsense. That's not true, right? Because you'll never get them the same as outdoors because you'd have to be outdoors to get them the same as outdoors. You will always have elevated levels of CO2 indoors over what you have outdoors. Because what do you got indoors? You got mammals breathing indoors, right? A lot of them, right? So they are contributing CO2. CO2 levels go up. If you completely closed up the building, the oxygen levels would drop, the CO2 levels would go way up, and so on and so forth. Anybody ever die? Well, we just talked about it downstairs. Anybody ever die from CO2, excessive levels of CO2? Not in an indoor air quality environment. Nobody ever died. Highest levels, we're going to learn that, put it in perspective, anything over 1,000, anything over 800 from an indoor air quality perspective, forget everything else, energy consumption, anything over 800. Anybody know what it is outdoors right now? What's the average CO2 levels outdoors right now worldwide? 450 is a little high. I would guess probably just about 400 now, maybe 390 or 400 worldwide. That don't mean it's 390 here because we got the Triborough Bridge going by, the FDR and so on and so forth. It might be a little bit higher, not a lot higher, a little bit higher here. What was it when I was born in 1910? Right? Huh? Probably about 325. What was it at the turn of the century? Right? Like 1880, 1890. It's 290. So what's happening to the CO2 levels outdoors? They're going up. Fossil fuel burning is raising the levels of CO2 in the air. And that's part of this whole global warming issue, right? Now, levels outside, let's say we can rely on them being somewhere around 400. What happens indoors? Indoors, the levels build up. There are people that have done research on this stuff, particularly American Society of Heating and Refrigerant Engineers. They have a standard for how to they have many standards on how to design air conditioning systems. One of them is on what you should use for thermal comfort. They're the ones that decide that it should be in the wintertime between 66 and 72. And in the summertime, it should be between 72 and 78. They're the guys that decide on what's acceptable thermal comfort. They publish a standard on it, what humidity it should be, and so on and so forth. They also have a standard, another standard on what amount of exchange with outside air you should have. They have another standard on what kind of filters you should use, right? So their standard for exchange with outside air says that we should have 15 to 20 cubic feet per minute per person in an environment like this. Every minute we should get, for each person that's in this room, we should be getting 15 to 20 cubic feet of outside air as part of the air that's coming into this room. Okay, so now what happens if you're getting exactly that amount? Does that mean the CO2 levels in here are the same as outdoors? No, because we're still producing it. It's just keeping them from going too high. They predict that the level indoors, in that situation when you're getting just their standard, that the level indoors will be 700 parts per million over what they are outdoors. So we would expect indoors they would not get higher. As long as you're meeting their standard, they would not get higher than, say, 1,000, 1,100 or something like that indoors. If it's getting higher than that, then that suggests you're not meeting their standards. Are we concerned about CO2 levels here because of the CO2 itself? No, we're only using CO2 to kind of estimate what the, we could get 2,000 and make any. I think the permissible exposure limit for CO2 is 5,000. And I think it can make you a little drowsy or something like that if you get that high. I mean, it's not really a negative health effects, but it might make you a little comfortable, like drowsy or something like that. Anybody ever see somewhere where they use CO2? I've only seen one spot commercially where they use CO2 in a product. I mean, they use it for soda, but where a worker might be exposed to the PEL of CO2. In the Diamond District, I once inspected a place where they would take diamonds with inclusions. Inclusions in diamonds are flaws. A lot of times, those flaws are little bits of carbon, like little black spots or brown spots or minerals inside the diamond. You got a black spot inside of a beautiful white stone, you're going to see it. It's obvious. What they would do is they would take a laser and zap that black spot, right? The only problem is when they zap that black spot with the laser, the diamond got very hot and exploded, right? So it doesn't do you much good to get rid of that little black spot, right? So what they do is they set up a system where they're blowing compressed CO2. They have cylinders of CO2, they're blowing CO2, and as it's expanding, it's getting very cold, right? In fact, you've seen sometimes they open CO2, you open it quickly and you see frost from the condensing, from freezing moisture in the air. So they're blasting these diamonds with CO2 while they're hitting them with this laser to burn out those inclusions. So instead of being black spots, they're now voids or white spots, right? And the workers that are doing it, if you can imagine, they're right on top of this whole process, right? So they are being exposed to a lot of CO2. So they need a hood or something to protect their exposure. Anybody remember someplace recently in the movies, real life, but in the movies, where there was an issue with excessive levels of CO2 impairing the functionality of some workers? Anybody see Apollo 13? You guys didn't see Apollo 13? Apollo 13 was the fourth, Apollo 11 is one that landed on the moon, but it was like one of the fourth or fifth actual missions to the moon. The earlier ones just went around it and came back, right? With mapping and so on and so forth. Apollo 11 was the first one to land. Apollo 12 landed, and there were a couple after Apollo 13. Apollo 13 didn't make it to the moon. They did make it to the moon, excuse me. They had an explosion on board, an oxygen tank. They were mixing there was in order to keep the tank from, I guess, condensing material or something like that, a little paddle in it. When they turned it on, it exploded, blew out the whole side of this module that was taking them to the moon. The lunar lander was connected to it still. They were just leaving Earth orbit when this occurred, and it exploded, damaged the system. They had to go into the lunar module because they were losing power very quickly. They needed power preserved in the landing module so they could come back to Earth and land. Right? They had to fire the retro rockets and so on. So they went into the lunar lander. That ensured that they weren't going to be landing on the moon. However, they didn't have the fuel or the energy that they would need to just turn the thing around and come back. So they literally had to go around the other side of the moon, and they didn't know whether they were going to have power to re-enter the Earth's atmosphere or not. They had They didn't know if they were going to be able to turn the computers on to calculate the re-entry angle so they wouldn't bounce off. And if you ever see the movie, this actually occurred back in those days. It was like 3 or 4 days that were like, very, very tense days in the space program. And they did a lot of remarkable things to, like to engineer a safe return for this. One of the issues that came up was that they were breathing into this lunar lander, and the device that would take CO2 out of the air, the CO2 filter, it might have been I don't know what was in it, it might have been permanganate or something like that, some chemical to capture CO2, take it out of the air, wasn't working, so the CO2 levels were building dangerously high. And they were most concerned because it would make them drowsy and lethargic and so on, and affect their judgment and so on and so forth, and eventually kill them if it got really high enough. So you literally, and part of the movie, a significant part of the movie is devoted to how to like use whatever pieces of duct tape and hose that they could find to like rig up this this substitute filter to take CO2 out and get it to work and so on, so they could come back, survive that and actually wind up landing. If you get a chance, I'm sure it's on Netflix. It's called Apollo 13. Tom Hanks is in it, so it's not a horrible movie, right? And it's really a really good movie. So get a chance, you'll see this environment that took place in this confined space has a lot of these elements, including the CO2. But at any rate, okay. So you want comfortable temperature, humidity, and so on and so forth. What's that? Oh, okay. Well, I guess you got to pay for it, right? It'd have to be on one of the other ones, pay like Amazon or something like that. Is it on Amazon Prime or something? I'm sure you can get it for a few bucks. You can rent it. You can rent not the low res. Yeah, I know I know what you younger people do. You steal this stuff anyway, so you'll just go online and go to a BitTorrent or something like that and grab it somewhere. So you don't necessarily you don't care about that, huh? You would never do that? Okay, good. There you go. You rent it for $2.99 on Amazon. That's the deal now. Huh? Oh, you mean in terms of the movie or renting it? Oh, okay. Sorry. Excuse me. Excuse me. There used to be this guy that used to come up to my window every time I got gas in Maspeth, selling me, like DVDs for $5. And some of them were pretty good with a bag. Yeah, some of them were actually pretty good, but a lot of them were like, people would get up and walk in front of it, and yeah, exactly. Some of them were a weird angle, like it's like you're looking up, like you're looking up Tom Hanks's nose and stuff like that. So some of them were worth it, some of them were not worth it, unfortunately. But at any rate, so we have parameters that we have standards. There are certain standards for indoor air quality, mostly associated with comfort. There's, unfortunately, in this country, not a lot of standards for anything else to do with indoor air quality. Mold spore counts, levels of VOCs, so on and so forth. A lot of people do these investigations, try and use the RELs, NIOSH RELs or TLVs or the PELs to kind of like give a perspective to their testing, but they really make no sense because most of this stuff in an environment like an office or something like that, if you were at 1/10 of the PEL, people are complaining. Carbon monoxide, if you're you would be very unusual, and you'd probably have a lot of associated odors and stuff like that if you had a process that was generating even 5 ppm of carbon monoxide in an office, and you would be getting some complaints from whatever odors were associated with it. But the standard, the OSHA PEL is 50, right? Most people use the REL, which is 25 now, but the PEL is still 50. Okay, so you don't see too much of that. So these are ASHRAE's recommendations for various things. So, and most of this is not really relevant to most offices. Carbon monoxide, yes, carbon dioxide, because you're using it for ventilation. Okay, temperature and humidity. This is their standards for temperature and humidity. Why? They give away right here. Wider temperature ranges differ for summer and winter. Part of it is energy savings. You don't want to heat more than you need to in the winter. You don't want to cool more than you need to in the summer. The other part of it is it's just a comfort consideration. You're wearing lighter clothes in the summer, so you can keep it. You don't have to get it as cool in the summer, and you can save a few dollars in the process. Same with the winter. Recommended humidity. Once you start getting over 50, 60%, you get into a neighborhood where the 60% humidity probably won't grow mold. But if you get to 60 or 70%, what might be going on that might grow mold? High humidity in the room, condensation. It's going to hit some colder surfaces, like in the wintertime, might hit the wall, right? The wall might be cold. You get condensation on the wall. Some ductwork, the diffusers have cold air coming in or something like that. You might get some condensation on the diffusers. Okay, we don't care about that. When I was young, they had this impression that we were going to be getting all our electricity from nuclear energy by the turn of the century, by the 21st century, and they were predicting. I swear this is the absolute truth, that electricity was going to be too cheap to meter. That's what they're predicting in those days. I'm not making that phrase up. That was a common phrase. Just like when computers started to become very popular, there was a notion that we would never need to use paper again. All I know is I'm using more paper than ever, because computers make it easy to generate paper, right? That's their best thing. OPEC. Anybody know what OPEC stands for? They're still around. They're kind of neutered quite a bit because there's so many other oil sources. Organization of Petroleum Exporting Countries. It's mostly North African countries, Saudi Arabia and Iraq and so on and so forth. They don't have the influence they had before because we have so many other sources of energy now. Venezuelan oil, the oil shale reserves and so on and so forth. So, but they were the primary producer back of oil in the 70s. They had the market nailed, and they decided, hey, we're not getting enough money for our oil, so we're going to raise the price dramatically and cut back on supply. This was the result. Oil became so expensive, and there were such shortages of oil that we couldn't get enough gasoline. And it got to the point where you could not get gas for your car. They would have lines that would go for miles at a gas station. I mean, miles for a gas station. Got so bad that they started rationing gasoline, that you could only fill up your car on alternate days, depending on whether you have an even last number or odd last number, odd and even days. This was really true. This went on for several months, maybe half a year. And so what happened is people got very concerned about energy in those days. And they started to figure one of the best ways to save energy is, among other things, use fuel more efficiently and tighten up buildings, more energy efficient design. One of them is to do less, you minimize the exchange with outside air. Okay. Now, sick building syndrome. What happened was that within about 5 years, people started to experience issues with the air inside these buildings that they hadn't experienced before, hadn't noticed before, and you started to get a lot of complaints. The term sick building syndrome started to appear. EPA defines that term as a building where more than 20% of the occupants are complaining. What's a building where less than 20% of the occupants are complaining? That's a nice building, right? That's really, most air conditioning contractors will tell you that at any one given time, you can only satisfy 80% of the people anyway. 20% of people are going to be too hot or too cold or too this or too that. So you can't satisfy anybody. So you shoot for those standards, attempting to satisfy as many people as you can. But if you got a building where 1 out of every 5 people is voicing serious complaints about the environment or claim that it's making them feel sick, that's what they call sick building syndrome. A lot of that can be nebulous complaints, very difficult to find complaints, headaches, itchiness, burning eyes, kind of hard to pin down what a source of those might be, and very subjective, very hard to measure. Not something like you can take a thermometer, stick it in somebody's mouth, and actually measure a temperature. It can be subjective. So if somebody doesn't like their work environment, they might be a little bit more sensitive than someone who has a good work environment. So it's very subjective. A lot of those sick building syndrome kind of things are very subjective. There's another class of issues that were raised also by tightening up these buildings. That's building-related illness. Difference between sick building syndrome and building-related illness. Building-related illnesses are specific diseases that are associated, like communicated by fresh air systems and so on, by indoor air systems. Okay, now we all know Legionella is one. Legionnaires disease is one of these building-related illnesses because it can be related with the air conditioning. The air conditioning system could be distributing the organism, or it could actually be growing the organism. Condensate fans or cooling towers. Usually not condensate fans because temperature's wrong. So here's our HVAC system. Here's another picture of an air handler, where you're cooling and heating the air, you're recirculating. You can see the exhaust air and the fresh outside air on those ducts, and so on and so forth. And this might be somewhat like what it looks like. Here's like the cooling cycle. That's kind of like what a compressor looks like. See that thing over there looks like kind of like a motor in the middle there. That's kind of like what a compressor might look like. Here's a cooling tower, warm air going in, a fan, pulling air past it. In this case, this is what they call a induced draft cooling tower. Fans on the top, it's pulling air in from the sides and then into the middle, and it gets pulled out the top. Meantime, the water's going down, dripping down through this fill. Okay, here's a system where we have those multiple air handlers. We've got a chiller sending cold water up to many air handlers throughout the building. Okay, and we're going to try and see if we can't get a visit, and at least look at some drawings, maybe a visit. Here's another system where you see a central plant with a chiller and air handlers with cooling coils, heating coils, and the air conditioning distributed to these various diffusers. Now that we're looking at this, there's another interesting feature about these systems, and that is 10 or 15 years ago, 20 years ago, most of these systems, the way that they work is a central plant produced cool air or warm air, sent it into these rooms with these ducts, and supplied air throughout the building at the same temperature. So maybe throughout the floor, because each air handler has a thermostat on it. And they measure the temperature coming back, and it would decide whether to cool it more or heat it more. Came out of these diffusers at the same rate, at the same temperature, all the time. That's called a constant volume system, right? And how does that work? Easy. You just have one fan. You have these things set with dampers set to deliver exactly the same amount of air at each one of them, 300 cubic feet per minute, 300 cubic feet per minute. And the air is coming through here and like just constantly comes through here at the same rate. It's constantly running. Fan never shuts off, runs all the time. Constant volume system. Problem with that is let's say we're on the sunny side of the building on a winter day. It might be warm in this room, and they're still sending warm air in here, so it doesn't get too hot in here. Conversely, if we're in the shady side of the building on a summer day, it might get too cold in here because it's sending cool air in here when we're in a warmer part of the building, a cooler part of the building, right? So what they do to avoid that is they instead put these things called variable air volume boxes, VAV boxes, up into the ductwork, and they're basically big valves, big dampers or valves, motorized. And they connect each one of them to a thermostat. And that thermostat controls that valve. So at any given time, it could be, if we need cooling in here, it can be wide open and air can be coming into this space. If we don't need cooling in here, it could shut that damper so no air is coming in here. What's the problem with no air coming in here? The temperature might be comfortable, but we're not getting any air changes. We're not getting any ventilation with outside air. So we start to build up that problem. Many of these early systems, they would actually shut down the airflow. So you get no air movement. They were very uncomfortable. What they did about that was they designed minimums into those things. So even though you're not getting what the architect would like you to get every minute, what you know, your 6 air changes per hour, they stay open enough and compromise the temperature enough that maybe you get 2 or 3 air changes per hour. So you still get some air movement, even if the temperature is satisfied, right? So those are called variable air volume systems. We got one here. That's a thermostat that's on the wall. It wouldn't be here if we didn't have a variable air volume system. Now, down in the labs downstairs, you may have noticed occasionally that some rooms would be cold and some rooms would be too hot, right? What's happening there is that the controls are not working properly. In other words, some rooms are getting too much cold air or too much warm air. Some areas getting too much cold air. It's that thermostat that's controlling that. And it may not be the thermostat might be right. Could be that damper is jammed or has some sort of problem, right? So those control it. Most buildings, one thermostat controls several offices, right? So one thermostat compare a whole branch of offices or something like that. So it's not like everybody has a thermostat in their office. Usually they put that in the boss's office, put it in the corner office, right? And he has control over what the temperature is. But they may affect joining offices. So he likes the air cold, and he calls the guy up for the AC unit and he says, hey, the building manager, hey, I want this room at 68 degrees, and you better keep it there, right? Then the adjoining 2 or 3 offices might be freezing, like you might be sitting there freezing because he likes the air cold, because they're controlled by the same thermostat. We have a bit of a luxury here when it works, not always working, that each one of the classrooms has its own VAV volume damper. So it should be perfect temperature in every room if we were working right. If the people that run the system actually knew how to work it. I'm going to delete that later on. So at any rate, that has an impact. These systems are very complicated. They're not always the easiest things. They can be ticklish too. They can have issues. So let's take a look at some of the issues that come up. Here's condensate pan, right, with mold and slime and stuff like that growing it. Slime is basically what they call a bacterial growth that's become so prolific that you have millions and millions of these bacteria, and they have like a slimy coating. They use to protect the cell membranes instead of cell bodies and stuff like that, and it forms a mass, and it kind of looks like snot, right? And one of the things that you'll see occasionally is you'll see one of these units, if it's in the ceiling, leaking, and that's usually because that snot has clogged up the drain line and caused the drain can to overflow and damage the ceiling tiles and so on. You'll see every once in a while. You go into a diner, almost any diner in New York, you go into a diner that's got air handlers in the ceiling, and you look up and you'll know where the air conditioning unit is by the stains on the ceiling tile. Right? And that's because the diner is handling a lot of food and stuff like that. It's scrubbing material out of the air. You got stuff growing in there. You get this bacterial slime or snot growing, and you got to call the air conditioning guy, and he blows it out. Sometimes, see this little thing over here? That's actually biocide tablets you can throw in there, supposedly kill that bacterial mass. That's assuming you like poison in your ducts rather than slime, but I guess it's a fair trade-off. This a condensate line right there coming off of a unit. So you'll see these lines coming off and usually go in the floor drains. This is also you can kind of get a feel for how these systems distribute either cold water or steam and so on and so forth. Okay, here's a high rise, multiple sections of the building, lower section of the building, upper section of the building, and so on. Okay, different kinds of fans. Here's the filter, standard air filter, a pleated air filter. It's a little bit more effective. Okay, some coils. There's a typical cooling coil with a condensate pan. It's got a little trap in it, to keep sewer gases from backing up into it and getting pulled in. Remember, the coils may be under a negative pressure. So that condensate pan's under a negative pressure, which means that pipe coming off of it is under a negative pressure, which means if you connect it to a sewage line, it's going to suck sewer gases out of the line and back up into the unit, right? So there's usually a little water trap before it goes to a drain. Humidifiers are a problem because you can grow stuff in humidifiers. And if you spray that stuff out into the air, you introduce it to the air and it can get throughout the whole place. And I think, no, I still got a few more. I just wanted to check how we're doing. Well, we're out of time. So, oops. So I'm going to kill it there. I suggest that next week I want to discuss how you would go in and actually test for this stuff, what kind of instrumentation you would have, what kind of equipment you would bring with you, how you would, maybe I'll show you a report, how you would prepare a report. So you kind of would be neophytes. In other words, between this and what we do next week, you would almost be in a position where you could certainly accompany somebody else that's done it before and kind of have a feel for what you're doing and why you're doing it, right? And if you really have no fear, you might even be able to fool somebody into thinking that you know what you're doing. Is that funny? Yeah, I got to tell you another story. Many years ago, I might have told you this before. Many years ago, I worked at a company where maybe I was about 3 or 4 years out of school, and a friend of mine came. They recruited him. He went to Clarkson University up in upstate New York. He came. He bought a home in New Jersey. He got married young, bought a home in New Jersey, and the bank. This is back in the late '70s. Bank told him, you know, we got this new thing we want you to do. It's called a home inspection. Right? You mean like an assessment? I got the assessment already. I said, no, this is something new. You call somebody up, they come in, they inspect the home for you, tell you if it's got any problems. Right? We want you to do that. This is new. Looked in the phone book, there were only like 1 or 2 guys doing this stuff in the phone book, right? It was really wasn't very widely done in those days. So he called the guy up, guy came over, charged him, I think, $100, $150. He went through a checklist. He was like basically a retired roofer or a carpenter or something like that. No, seriously. Well, the guy knew about homes. You know, like he worked in the construction industry. He knew homes. He walked around with him, went through this checklist, gave him the checklist, signed his name, handed it to him, give me a check for 150. Right? He came in all excited the next day. Tony, we got to do this. This is great. Right? So he talked me into starting a company with him, and we did home inspections for 15 years. He may still be doing it. We did it for about 15 years. Eventually, I moved out to Queens. Most of the work was in New Jersey, so I like bailed out and told him, so your this terrific operation we have where we do about maybe 3 or 4 days a week. This great operation where we're making a fortune. We made nothing, but we would make $100, $200 for a home inspection. It would take us 2 or 3 hours to do the inspection, another 2 or 3 hours to do the freaking report. We'd be pulling in maybe 150 or something like that. The real estate agent would show up to the same house drunk and make $5 grand. So it was a very depressing environment, but we loved doing it because every house was different. It was really interesting. We really loved doing it, right? So the first job we did, we had no clue what we were doing. I was mostly mechanical. I knew a lot of mechanical, and in my college, I did a lot of mechanical engineering and stuff like that. And I knew HVAC system, electrical system. He was a civil engineer. He knew structures, roofs, and stuff like that. Like buildings. And the two of us were in pretty good shape together. We found the one book at the library on home inspection. One book, that is 100 books. Those shelves of books. One book back in those days. We read that book. We both read that book. We got old, and we so didn't want to look like idiots that we showed up to this house we were going to inspect the day before we inspected it, and we scouted it out from the outside with binoculars. So we would at least kind of have like some idea what to start with, because we usually start on the outside. Right. And for the first year, we did everything together. And he would learn mechanical and electrical systems from me, and I would learn the structural stuff from him. And by the end of the first year, we really pretty much knew our stuff. We were pretty solid with this stuff. But that's your situation. I mean, you have to have a little bit of confidence that, if I don't know it all, I'll figure it out. So when you go on your first indoor air quality assessment on your own, hopefully you get the opportunity to work with someone that has done it before. But when you go on one of these things on your own, you'll have a little bit of a background on what to expect, what to look at. Let me see the drawings. You can at least look at them, go through them, make believe you know what you're reading. I'm going to bring in some drawings next week so we can go through them. So next week is going to be, what do I do? I show up to the building. What am I going to do? Look at the drawings. How do I look at the drawings? What instrument am I going to use? How am I going to measure CO2 levels? Where am I going to go? What floor am I going to? What questions am I going to ask? Right? So that you guys get kind of and then see what kind of a report might look like. They don't all look the same, but it should be interesting. Okay. Give me